Welcome back. We're going to be picking up a little bit of where we left off in the last uh, lecture, where we started to talk about the iron carbon phase diagram and important attributes of that and how microstructures developed in steel. So we're going to be moving on to a little more of the practical application of the iron carbon phase diagram, and that mostly involves what we consider the heat treatment of steels. So it's an important enough topic that we're going to divide it into two parts. And so this first part, we're going to talk about more isothermal transformations, or transformations that occur at a single temperature, where what we're changing is the time that we're holding the steel at that temperature. And then we'll move on to continuous cooling and concepts of hardenability as we continue to move through. So as we move forward, we start with our quote of the day from Charles Kettering again. And I like this one. When you get into your working lives, people are going to tell you that we've done it this way for 5, 10, 20, I've heard 30 years. We've been doing it this way. Well, in some cases, it's probably wrong because things change. New technologies come about. So if you've done something, always done that way, in a lot of cases, probably wrong. So what we're going to talk a little bit about is isothermal transformation diagrams in this time. And I'm going to talk a little bit about how these were formed. These are what we consider to be time temperature transformation diagrams, or TTT diagrams. And what these are these incredibly invaluable tools in the heat treatment of steels. And as we sort of mentioned a little bit in the past, but we didn't really get too much into it, was that steels are very unique because their processing history can significantly change their properties and performance. One single grade of steel can be processed in a number of different ways and give you a fairly wide range of properties that gives it that flexibility that we see in steel that allows it to be so widely used. But what we're going to also see is when we hold these steels for different periods of time and we process them differently, is that there are other micro constituents. These are not phases, because phase diagrams, as we remember, occur at equilibrium. So they're equilibrium phase diagrams. So the perlite, the ferrite, the austenite, those are equilibrium phases. Now there are other micro constituents we're going to run into. And probably the most important of these is martensite. And that transformation is different. The other transformations that we're talking about are governed by nucleation and growth and their diffusion-based transformations. Martensite is different than that. Martensite is athermal, and it's a stress-induced transformation. So we're going to talk a little more about that, and then how these microstructures develop, how we can use these tools, this TTT, or these isothermal transformation diagrams, to understand how microstructure develops and be able to design heat treat cycles that will allow us to produce these different microstructures and steels with different properties. So current readings, highly recommend that you go through just those 10 pages for chapter 10. And as part of your homework for lesson 8, these two are assigned problems, and I recommend that you do all of these as we've done. And as we've done throughout the course, at the completion of the lesson, all of the solutions will be posted on Canvas. So we see that we get some other important terminologies that tend to come out as we start talking about these different heat treatments of steels. Perlite we're familiar with, but different morphologies of perlite, whether it's coarse or fine. Bainite is one of these microconstituents. Spherodite is, as well as is martensite. And we're going to see that martensite is different in that it has a start and finish temperature. And we're going to cover these in a lot more detail as we move forward. So let's go back a little bit, back a lesson or two, where we're talking about the kinetics of phase transformations. And we know that growth, or these types of S-curves, as we call them, are what we consider Avrami S-curves. We see how the slope changes with temperature, how that nucleation, higher temperatures give us longer nucleation. Remember, we needed undercooling for nucleation to occur. But we had these curves, and these curves are representative of, each curve represents a single temperature for an alloy. And so we can understand a little bit of what that rate of transformation is from that nucleation and growth perspective. And so we can collect these data, and these were done in what's considered a Jominy end quench test. And we're going to see how that is done, or through a wide range of heat treatment cycles. And so they maintain a temperature until the transformation is completed. So it's isothermal transformation. And all of these transformations occur from a sample that begins at 100% austenite. Now we saw, as we remember right, we're going to start in the 100% austenite range at about the 925 degrees C range, and we'll cool it from there. Now, with that decreased undercooling, we see how the rate of transformation will change over time. And so increasing temperature, decreasing undercooling will slow that rate of transformation as we move through. And so with that, what we ended up with, and in the steel industry, this goes back to a very famous metallurgist. His name is Edgar Bain. He worked at U.S. Steel and a number of different steel companies, but he was fascinated with the nucleation and growth, or this what we would consider to be the decomposition of austenite into perlite and other microconstituents that we're going to see. So he and other researchers at U.S. Steel, and this was down in Monroeville at sort of the heydays of the steel industry, they were looking at these transformations, and there was no easy way. They would have, for each steel, they would have probably hundreds of these different types S-curves. And they were very difficult to sort of combine and to understand. And so there were a lot of, U.S. Steel didn't want to be in the heat treatment of steel business. They wanted to make steel and sell people to others to use. That's where their business model laid. And so with that, they really started giving some thought to how can we make these S-curves, or this combination, this hundreds of S-curves that we have and all this data, how can we develop a useful tool for people in the heat treat business or people who are processing steel to be able to use it? So for the most part, so they quit calling up U.S. Steel with questions. And so this really was a clever, innovative, very engineering elegant way to look at it, because Bain and his other researchers really gave thought to, so heat, what at the essence is the heat treatment of steel? So what do you need to know? Really, you need to know two things: the time that you're going to hold it and the temperature at which you're going to hold it. And so they said, well, we have the time. This percent transformation tells us a little bit, but we need to find a little better way, because temperature is our other one. So what they started to do was they said, okay, so we know time and temperature, so let's plot the 0 point where the transformation begins, the 50%, and where the transformation ends. And so what they found was that changed with time. So at each temperature, they ended up with a horizontal line across here with these points. And as they took all of their curves, they started to see a different type of curve appear, which is this, what we're going to see is more of a C-shaped curve. And so they were able to really distill a lot of information into a single plot. And that's really where engineering elegance tends to come in. And they started with if we start with just a eutectoid steel, which if we remember is about a 1078 steel, 0.78% carbon. And we have austenite to perlite transformation. And so we know that it will occur given time, but there's time required for that nucleation to occur, especially as you start undercooling. And we see as the undercooling goes, the time for that transformation to begin becomes lower and lower. And so what they were able to do was start creating these curves. And so they started looking at them and knowing where they started and sort of getting an idea of how the microstructure would evolve over time, given that TTT curve. Now, these are fairly easy to read because they've distilled so much information into a fairly simple combination of just time and temperature. So we know in these plots that everything starts with austenite. We talked a little bit in the past that austenite is this great eraser. If you make a mistake in the lower temperatures, all you need to do is heat back up into the austenite range, and it erases all those mistakes that were made. But as we're thinking in cooling, we always start with austenite. And as I said, we start at about 930. And what we have to imagine is that we instantaneously cool that down almost at 0 time and then hold it at a given temperature. And that's sort of where these time temperature transformation, or these isothermal transformation diagrams really begin, where we have a single temperature that we're interested in, and we're going to hold it for a specific period of time. So in this case, let's start at our 930 degrees C, and we instantaneously drop to a temperature of 625 degrees C. And we hold it for a period of time. Now, this line represents where the perlite, or the transformation of the austenite to perlite, will begin. And so until we reach that time, see at 1 second, nothing happens. And since this is a logarithmic scale, we're probably at about 3 seconds, 2 or 3 seconds. We run into this line that represents the beginning of the perlite transformation. So we're going to start forming perlite. And as we continue on to about 5 seconds, what we tend to see is we're about halfway. That's what the dotted line here represents, the 50% point for the transformation. And then once we reach the green line here, or this point D, we reach completion in about 15 seconds. And so with that, we have a completely perlitic microstructure because this is a eutectoid steel. And so with that, what we see is really the transformation of this material at 625 degrees C, and at about 15 seconds, we go from pure austenite, holding it at this temperature, to a completely perlitic microstructure. Now, what if we're up here at 700 degrees C? What we tend to see is we have to hold it almost to 100 seconds before we even begin to form the transformation. And what we tend to see is it takes a much, much longer time for it to actually reach a transformation at that. So the austenite is very stable up at these higher temperatures. And so the perlite transformation takes much longer. Now, if we're going to have that much time and temperature, it goes to reason that the perlite is going to actually look different. And perlite at these higher temperatures is what we call coarse perlite. So we have coarse perlite at these high temperatures and long times, and fine perlite at at these higher undercoolings or lower temperatures and shorter times. And so this coarse perlite and fine perlite is really a sort of a thickness ratio. We know that the perlite is a lamellar type structure. And so this thickness ratio between the ferrite, which is the light region, and the cementite, which are the dark bands here, is going to change. So with coarse perlite, there's more time for diffusion to occur, higher temperatures, longer times. And so the carbon diffusion can go over longer distances. And so they form these thicker, what we call lamellar, between the areas. So we have relatively thick layers of perlite and cementite. Now in fine perlite, this is going to occur, and if we go back to this plot, we tend to see the fine perlite tends to exist at this area where the curves are starting to become more vertical, where they curve down almost in this vertical area here. So we have a fairly well-defined, fairly short period of time in which the perlite is going to transform. And so with these lower temperatures, shorter times, we have lower diffusion rates. So the carbon doesn't have as much time to diffuse at certain distances. So the layers are thinner, they're a lot closer together, and so they form at these temperatures. And so we get this coarse perlite and fine perlite area. And as I had said, as you change processing conditions, you change properties. Coarse perlite and fine perlite have significantly different properties. And as you would imagine from when we talked about Hall-Petch type relationships and grain size impacts on yield strength, we're going to see that the fine perlite tends to be a lot different and what we would consider a lot harder, a lot stronger than what the coarse perlite would be. Now, we can also use these curves to start to understand pro-eutectoid constituents. In this case, we're taking a highly hyper-eutectoid steel at 1.13 weight percent carbon. And so this would be, for the most part, some type of very hard cutting steel. And so at compositions above the eutectoid, we would form pro-eutectoid cementite, right? It's a hyper-eutectoid steel. Now, the same thing would occur with a hypo-eutectoid steel, except that pro-eutectoid phase would be ferrite in this case. And so what we start to see are these curves that form. Now, when you see these curves, they're typically going to be labeled in this way, where it's cementite plus austenite. And we know we're not going to form 100% pro-eutectoid cementite, but the transformation will reach its completion after a certain period of time. And that is primarily based on how much cementite we would be able to predict from the phase diagram. So we would go back to the phase diagrams, know that we would produce a certain amount of proeutectoid cementite in at that temperature or right below the eutectoid. And so from that point, we would see how that would form, and then the perlite transformation would start. Because as you go across here, until you reach this completion, any amount of austenite left can still be transformed. That's going to be an important consideration as we move forward. So what we see here, these are the equilibrium phases that we would tend to see. And even in some cases, these equilibrium phases can take on different morphologies. And so we have proeutectoid phases and the perlite, which is the combination of ferrite and cementite.